Thank you all for joining us today. We are having our regional talk number 6 for the year. Today's talk is focused on upgrading of buildings, bridges, and structural components through the use of fibre reinforced polymer technology, where high tensile strength, lightweight fibres, and proved durability are required. Today we've got Ahmed Sobhy joining us to talk on structural strengthening. He is a specification manager for Fibre in the UK. He is a qualified civil engineer with an MBA degree from the University of Exeter in England, and with more than 10 years of experience in construction material specifications across the Middle East and more recently Europe. So without further ado, I will hand over to Ahmed. Thank you so much.
Thank you very much, Fiona. Good afternoon, everyone. It's a pleasure to be talking to you today. It's an absolute honor. Thank you very much, Fiona, for the opportunity to be speaking to this very professional, fun crowd today. I'm hoping that by the end of the presentation, for anyone who is hoping to learn a little bit about structural strengthening, obviously this is going to be an introductory bit. There's a lot more detail that cannot be covered within an hour CPD, and this is why we always keep the door open for a bit of questions towards the end, and also our door is open absolutely all the time with emails and phone calls if you need any further clarifications. As Fiona said, my name is Ahmed. Thank you very much for the introduction, Fiona. I'm the specification manager of Fibre here in the UK and Ireland. My job in a nutshell is quite bridge gapping what you guys as civil engineers and specifiers kind of want to achieve in site, and also what can be realistically achieved in terms of materials and solutions, but also from the other side, when something is being cooked from a manufacturing point of view, something is being prepared, is also to deliver that technology to you. And this is why structural strengthening using FRP is one of my most interesting topics, because it's a topic that is not nearly finished. It's always under progress, always under study, and nowhere near maturity. And this is why it's a very, very interesting topic to discuss. Our agenda for today, don't be really discouraged by the heavy content that you see in front of you. It's quite a straightforward presentation, a straightforward CPD. We are going to talk very briefly about the company, what Fibre do, just in case if no one has come across Fibre before, which is absolutely fine, obviously. We're going to introduce the epoxy resins and the different fibre types. We're going to talk to aim to answer the question, why do we strengthen and why do we use FRP? And a bit of a disclaimer before we get into a lot of details here. This presentation is not aimed to tell you that using FRP is your one-stop solution for literally anything related to structural strengthening. As any system, as any material in the world, it's got its own limitations. It's got its own limits. So obviously it can be used when appropriate, and we'll point that out when we talk. But also it can't be used when it's inappropriate. And we also talk about a few instances where this is not going to be possible to use FRP for structural strengthening. And then we're going to talk about a bit of an interesting topic, externally applied fibre reinforced polymers and the comparison with the near surface mounted application. We're going to talk about a few of the application and case studies, some of the application guidelines that are available out there in terms of standards, and then the design and inspection standards finally. We are going to aim to finish within 50 minutes and leave 10 minutes for question and answers. However, if you do have a burning question within the presentation, please feel free to ask. A bit about the company. Fibre is a company that is present at the minute in about 61 countries. We employ 10,000 employees at the minute, and the most important thing that we have 10 research centers across the world. This is how the company is actually dedicated towards research and development, and this is a topic that we will touch on later on the slides when we talk about very briefly sustainability. Fibre is generally a part of a bigger umbrella, a bigger group called Saint-Gobain. I'm hoping that the name rings a bell for some of you, but we are owned by a company called Saint-Gobain. If the name rings a bell, we are sister companies with the likes of British Gypsum, the likes of GCP, Sterling Lloyd. We're all under the same umbrella of Saint-Gobain. Saint-Gobain operates in about 76 countries across the world, with about 166,000 employees. I'm thinking that also Saint-Gobain operates in South Africa, but I'm not quite sure. Our core range, and this is specific to the UK and Ireland market. My apology, this presentation is kind of tailored towards the market in the UK and Ireland. Obviously, the technology, the information, the knowledge is quite common, so it can be transferred from here to South Africa, definitely, but the market information is quite targeted towards the UK. So we serve the market here in the UK and Ireland through 5 main pillars that you see in front of you. Our biggest pillars at the minute, our core range of products is external wall insulation and renders, which obviously forms a huge part of our business. We also have a flooring range. So obviously when talking about your screeds, your self-leveling or self-smoothing compounds, we also have a tile fixing range. And lastly, my part of the business is the technical mortars. Again, quite relevant to the people who have relevance in the UK market or who operate in the UK market. We've got 3 plants across the UK and Ireland. Our head office and main plant is based in Flitwick, Bedfordshire. We've got another plant in Telford and the 3rd plant in Northern Ireland in Ballyclare. We try as much as we can to source our material locally. As a part of Saint-Gobain, we've obviously got sustainability at heart of any business that we do, and we've got our net zero targets. And with these 3 locations kind of centrally located within the UK and Ireland, we kind of have better control on our supply chain, which obviously forms a huge contribution into the carbon emissions that we make. Also, from a supply chain perspective, we try as much as we can to locally source our raw material and our products in order to minimize the carbon emissions related to raw materials and production. When we talk about the market and the technical mortar market, basically we use the terms infrastructure and technical mortars in kind of a synonymous way, because at Weber in the UK we highly focus on the infrastructure sector of the construction, and we serve this market through 4 main pillars of product portfolios. The first of them being the concrete repair. Obviously a huge range of products that has a dedicated CPD towards it on its own. But as you can see from the picture here, obviously a big part of it is the spray concrete with its massive and different applications, whether for slope stabilization, impressed current systems, or also repairing big cracks. We also specialize in precision grouting. Obviously, a big range of our products is targeted towards precision grouting, whether that is in an infrastructure context or a bridge context in terms of bridge bearings and plinth, but also from an industrial context when we're talking about machine-based plates. Thirdly, highway mortars forms a big part of our business as well. So we're talking about patch repairs, obviously for different thicknesses and different bay areas, quite fast-setting materials that serve obviously the highways. Also, the bedding mortars that kind of serve the furniture of the highways. And lastly, our topic for the day and a huge area of personal interest of mine is the structural strengthening using fiber reinforced polymers. Moving on to the introduction about the epoxy resins and the different fiber types. As we talk about, for instance, reinforced concrete, we're talking about a composite section where concrete and steel come together for obvious reasons that we all know about. In kind of a similar way, when we talk about fiber reinforced polymer, we're talking about a composite material that is made of a polymer matrix in addition to fibers. The fibers at the minute they can be a myriad of materials. Obviously, glass, carbon, and Aramid or Kevlar, as they call it, is quite common materials. But as we explore more, as we research more, and obviously as we focus more on sustainability, a lot of material comes to the front, and one of which is obviously basalt, which is a material that is highly researched at the minute. I think there's a question here. Third question. Sorry, you have no sound. Fiona, can you hear me, guys?
Yes, we can. Maybe if he can just leave and join again, sometimes that fixes it. I know I have that problem on Teams sometimes, so yeah, I think we can all hear you. Yeah, thank you.
Thank you. All right, moving on. As we said, as we kind of address sustainability issues more and more, a lot of material a lot of fiber types come to the front, and lastly basalt, which is obviously a material that is kind of researched and studied at the minute for use in fiber in structural strengthening. When we're talking about the polymer matrix, the most common material that is used at the minute is obviously epoxy, the epoxy resin, but there are other materials that can also be used. We will talk about about the epoxy resin in the next slides and why is it of importance. We're quite aware that epoxy resins, or epoxy in general, is a petroleum derivative, and as a company and as an industry, we should be very much aware about the carbon emissions and the downfalls of using petroleum derivatives into obviously the fiber reinforced polymers or construction in general. We're very much aware about this. So when we're talking about, for instance, a laminate or a finished product of fiber reinforced polymer, we're talking about a resin to a fiber to resin ratio of about 60-70% to 30%, obviously fiber being the 60 to 70%. And with that low proportion of resin within the plate or the finished laminate, obviously it has the highest contribution of carbon emissions when we talk about life cycle analysis over the life cycle of the product. So when we're talking about this 30% of resin contributes about 80% of the carbon emission of that product over its life. So obviously it's a huge contribution when we're talking about carbon emissions, and we're quite aware about this as a business, and we're always investing into finding alternatives of epoxy. But I think you guys would agree with me that adopting new technologies within the construction industry is not the easiest. There are lots of obstacles and lots of hurdles to go through in order for this to be to find its route to market. But we are the most important point that we're aware about this, and we're doing our best actually to change that moving forward. When we're talking about the resin, the fiber reinforced polymers as a material in general, obviously it's not kind of exclusive to the construction industry. It has been present before the construction industry, has been used in several other industries, and the main two reasons that it's been used in different industries is it's lightweight, number one, and number two, its ability to take a massive amount of load. So as you can see from the pictures here, it has been used obviously in the manufacture of spaceships and space shuttles, also in racing cars, but also from an army and military point of view, it has been used heavily, especially Kevlar, to produce bulletproof vests. Also kind of strengthening the point of the resin properties, and why is it of huge importance that we give significant importance to what material, what resin type that we actually specify. The reason why is that of importance is when we're talking about fiber reinforced polymers used for structural strengthening generally, we're talking about the loads and the structural elements are being transferred to the fibers actually through the resin. So obviously we're talking about a load-bearing element that needs to have minimum viable mechanical properties in order for it to be to transfer the loads from the structural element to the fibers. That's number one. Number two, when we talk about the most common means of failure, especially right after the application of fiber reinforced polymers, it's usually due to delamination. Obviously, delamination could be due to several reasons. One of them is the poor application of the material, but also from research and from various experiences, the poor properties, the poor mechanical properties of resins that have been used could play a major factor in delamination of fiber reinforced polymers after application. And this is why it's very important for us to give huge significance to the resin type and the properties of the resin that we produce. The resin that you can see in front of you is in full accordance with part 4 of BSEN 1504, which is related to structural bonding. Obviously, BSEN 1504 is a harmonized standard. I don't know if it's relevant in South Africa, to be completely honest, but it is it's the harmonized standard, the most governing standard when it gets to concrete repair and protection. And part 4 of that specification of that standard covers the structural bonding. From a general perspective, when we talk about Weber structural adhesive, we're talking about early strength development of about 70 to 80 megapascals within 48 hours. We're talking about a very low shrinkage material, and that is of very high importance because the fibers themselves as material are very low in shrinkage. So when we combine them with another resin or another material, they need to match their low shrinkage properties. Otherwise, this will cause strains within the finished laminate, unnecessary strains, basically. The last and most important point, in my point of view, is that this material is a moisture tolerant material. Obviously, it's a good practice for us to apply this material when the moisture content does not exceed 4%. But we're talking about the moisture content. Is there a question? Sorry. We're talking about the moisture content.
No, carry on. Sorry, no questions.
That's
Cool.
really fine. That's absolutely fine. We're talking about the moisture content within the concrete, but in a country like the UK, and I'm supposing tropical weather in South Africa as well, if we've got dampness on the surface of the concrete, this is absolutely fine also to apply Weber structural adhesive on top of it, because it's a moisture tolerant material. When we compare that from a general perspective with the cement-based concretes, cement, as we all know, it needs about 28 days to gain strength, unless certain special admixtures have been used on it. We're talking about lower strength gains. We're talking about 30 to 60 megapascals over the period of 28 days. We're talking about the need, obviously, of form work, obviously, which goes hand in hand with using cement-based concretes. So moving on, obviously, to the different fiber types that we have within our range. We've got the glass fiber that comes in sheets. We've got the carbon fiber that comes in both forms as plates and sheets. And also we lastly have the Aramid fiber sheets. This picture that you see in here, just a minute. This picture that you see in here for the Aramid fiber sheets was applied on the M6. I'm sorry again. This is a project that happened on the M6 here in the UK. If it's irrelevant to you guys, my extreme apologies, but you'll take the gist of it. Literally, a military tank was actually passing by, and this wasn't the first incident. This column on the road on the M6 was actually quite susceptible to lots of impact, obviously, by cars. And the reason that caused the application of the Aramid fiber on this column was a military tank that has actually hit the column, which caused severe deterioration. And in this instance, in this application, it wasn't structural strengthening, rather it was concrete protection of the and impact resistance of the concrete column. So this is the range that we have at the minute. Obviously, the specification of which material and what can be used in what application definitely depends on many criteria, and we'll try as much as we can to kind of summarize this in the next slides. So talking about the different mechanical properties, we will single out a few of the product portfolio that you've seen in the previous slide. If you start by the carbon fiber, for instance, and the picture that you can see in here is obviously kind of a column strengthening and axial reinforcement for a column to increase its load capacity. So if we talk about the mechanical properties, we're talking about a sheet weight of around 200 to 400 grams per square meter. Obviously, this is a very low weight, especially compared to our regular kind of day-to-day material that we use in construction. It's a very low in weight material. We're talking about a tensile strength of about 2,600 to 4,400 megapascals. And I think it's quite important for us to note here that when we're talking about the tensile, these numbers, these values for tensile strength are basically for the fibers. They're not for the finished product. So when the fiber is combined with the resin, these numbers actually reduced dramatically. That's number one. Number two, even when we consider the tensile strength of the finished product, the laminate or the wrapping, we don't really take the whole amount of the tensile strength in our design and our consideration. We take only a proportion of that, and as you will see later on the slides, the most governing criteria will be the strains rather than the stresses, because this material, we don't forget, we must always keep in mind that it plays a part within an ecosystem of concrete, and obviously the concrete within the system is the weakest component. So we can't design according to 1,000 megapascals or 1,500 megapascals. We only take a portion of it. Otherwise, the concrete will completely crush, or the system that we design will delaminate. And as we'll compare later on, the governing criteria when we're designing will be mostly the strains rather than the stresses. One of the most important pros when we're talking about carbon fiber in general is that it's not really susceptible to creep. So when we're talking about the sustained loading, an application where sustained loading is in place in action, we usually specify carbon fibers. On the other hand, one of the cons of carbon fiber is that it's a conductive material. So obviously we need to be very much aware when steel comes in contact with carbon fiber, for instance, because that will initiate a corrosion cell. So we need obviously to apply kind of an insulation layer. Moving on to the properties of the glass fiber, not really dissimilar from the carbon fiber that we've seen previously. We're talking about a sheet weight of 350 grams per square meter. We're talking about a tensile strength of 2,850 megapascals. before we move on, my apologies, before we move on, obviously it's important to note that when we're talking about fiber reinforced polymer family in general, apologies, we're not talking about the most ductile material ever, and this will be evident when we compare the stress-strain curve and the performance of the material, the behavior of the material under loads. So we're talking about quite a ductile, so quite a rigid material, so we don't expect a huge amount of elongation. And again, this is one of the main reasons why the design is actually based on strains rather than stresses. So for this specific material, the elongation of rupture is about 2.8%. Moving on lastly to the Aramid, again, not too dissimilar from the previous families. The sheet weight is about 320 to 450 grams per square meter. Tensile strength is 2,900 megapascals. Elongation is about 2.3 to 2.5% at rupture. So if we try to kind of summarize the different properties that we've seen earlier and kind of put it all together in a stress and strain curve to put things into perspective, and also it's quite important for us to understand the behavior of these materials when we're designing, and also compare it to the most common material used, which is obviously the reinforcing steel. As we all know, the reinforcing steel has got a yielding point. Prior to the yielding point, the performance of the steel under load, or the behavior of the steel under load, is quite elastic in nature, and after the yielding point is quite plastic. As you can see from the different fiber types in here, they've got absolutely no yielding point whatsoever, and they're governed by quite a very elastic performance, elastic behavior under loads. Obviously, they can take a huge amount of loading, as we can see, obviously, especially compared to reinforcing steel. However, the rupture is quite brittle and it's quite sudden. And this is something that we need, obviously, to take into consideration when we're designing. A very important point also to note that, for instance, because the fiber reinforced polymers in general are quite governed by an elastic performance, they're quite handy when we're designing for things like seismic loading, for instance, because when the load hits, and as soon as it's released, the fiber reinforced polymers, they kind of go back to its original form, to kind of to where it started, because again, it's covered by an elastic performance. This is why the majority of the design, the majority of application that we use fiber reinforced polymers for are to take the live load actions, because they take a huge amount of load, and obviously the load is released, the fibers, they kind of go back to its original form without any deformation. So a bit of a selection criteria to kind of, again, summarize what we've talked about before. If the governing criteria, if you want to achieve stiffness, and it's also quite important to note that one of the limitations of using fiber reinforced polymers in structural strengthening is basically adding a lot of a stiffness, or actually defying deflection. This is one of the limitations. As I said in the beginning, fiber reinforced polymer is not a one-stop solution for everything. It's got its own limitations, and one of them is actually deflection. The reason being is the very low thickness of the material. So when we're talking about plates, for instance, we're talking about 0.1 millimeters, we're talking about 0.3, 0.4 millimeters. So the thickness itself is very, very little. So it doesn't add much stiffness to the structural elements. Obviously, when we want to increase the stiffness a lot, for one of the applications is obviously to kind of control deflections. We usually specify steel plates, and we still get involved with the specification of steel plates because they're usually installed and fixed using structural adhesive. When the objective is actually increase the ductility, we usually specify glass fiber sheets or Aramid fiber sheets. As we discussed earlier in the application on the M6, when the objective is actually to increase the impact resistance or the blast resistance, the majority of applications are going to be either Aramid, which is quite heavily used in these applications, or glass fiber sheets. Moving on to the most important point in my point of view, why do we strengthen and why do we use FRP? In this part of the presentation, we're going also to talk about some of the feasibility studies and the different options that we go through whenever we're coming up against a structural strengthening project. So why do we strengthen? Obviously, there are a myriad of reasons why do we strengthen. The most important, the most common, in my view, is the inadequate design. We we got involved in numerous projects where inadequate design has been in place, and obviously the designer, to kind of make up for the problems that has happened during the design, they opt for structural strengthening using fiber reinforced polymers. However, again, as we talk a lot about sustainability, and as it comes to the front more and more, we're talking about repurposing our structures and kind of reusing our structures rather than demolition and building again. So obviously one of the main applications where we use structural strengthening is also repurposing or change in use. So let's say a multi-story car park that is being repurposed into an office building or whatever, so for which that we need to increase the structural capacity of certain members. This is when we use fiber reinforced polymers for structural strengthening in general, not fiber reinforced polymers. But also we've got involved in many applications where the damage risk has been there, and one of them is the project that we've talked about on the M6, and also the risk of explosion or impact damage has been in place. So in these instances, it will be more of a protection to the structural element rather than it is structural strengthening. Moving on to a bit of the different options that we have when we're up against any structural strengthening project as a project manager, as a designer. The majority of the options that you will actually study or think about are actually here. We try to consider them as much as we can to kind of give you an image of the pros and cons of using FRP for structural strengthening. So when we're up against a project, we usually kind of go through three main routes. It's either casting new reinforced concrete sections, or as we call in other terms, jacketing or member enlargement. We also have the option of steel plate bonding. And lastly, we've got the FRP strengthening. If we start by the first option that we see in here, obviously talking about sustainability, we're trying as much as we can to kind of drive the point that we need to cast less concrete as much as we can because of obviously the carbon emissions associated with casting new concrete. However, if we put sustainability aside for a minute, obviously casting new concrete comes with many disadvantages, and we're definitely aware about them. Obviously, it's a very highly labor-intensive process. Obviously, it needs 4 more props, and obviously there is loading restrictions during curing. So obviously, it takes a huge amount of time and preparation, and quite labor-intensive process to be established. When we move forward, obviously, to the second option, which is a steel plate bonding, which has been used for structural strengthening for a very long time. And again, this is nothing against using steel plates. It is a great application, a great solution when appropriate. Also, one of the solutions against deflection is obviously using steel plate. And again, we get involved a lot with it, but it is to tell you that there are other solutions rather than steel plate, and also to kind of open the door to the disadvantages of using steel plates, as we can see it here. Obviously, we've got handling issues. This material is quite heavy, it's steel, so it needs obviously machinery to be lifted and placed. Also, we've got like a complex fixing systems that uses adhesives as well as anchor bolts. And obviously the material, because of the main reason that it is steel, it needs protection and maintenance. When we move forward to the FRP strengthening, we're talking about basically a maintenance-free system once it's applied correctly. It's applied correctly and obviously applied by the right labor, by the right contracting company. And this is why it's important to use skilled laborers in this application. This is, I think, in my opinion, 80% of the success goes to surface preparation as well as skilled labor. However, this process is very lightweight in application, very cost effective because it saves a lot of money. So when we discuss obviously the whole life costing of the project, this is definitely lowest and lower in cost than the other alternatives. Moving on, this is a case study that we have done before in Harbour View multi-story car park. As you can see from the picture here, a part of the building was actually demolished. I don't recall the reason for the demolishing, but a part of the building was actually demolished, which has increased the loading obviously on the existing structural members. In this instance, obviously the designer opted for using fiber reinforced polymers for structural strengthening. And as you can see in here, the plates, the carbon fiber plates are being, it's a double layer, it's 2-layer of fiber reinforced polymer, carbon fiber reinforced polymers being applied under the soffit for flexural strengthening. and in here the application of carbon fiber wraps for shear strengthening. And as you can see, it's quite interesting that they actually applied in kind of the same terminology as we use steel and stirrups. So this U wrap is acting as a stirrup, so obviously it needs to be applied on top of the plate, not the other way around. In this slide, I'm going to show you a video. We tried the video before the presentation. The sound didn't work, which is absolutely fine. It's completely irrelevant. What I want to show you is the actual application of the material and how it is applied. Sorry. Quite an interesting application. I think it was quite evident that obviously because of the very lightweight of the material and in an overhead application like this, it was very, very convenient to kind of hold the material overhead and kind of apply it and also bend it, which was quite maneuverable. Absolutely really, really convenient in this kind of application. If we have considered obviously using steel plates, for instance, in this application, it would have been a lot harder than picture that we have seen here in the video. So kind of to summarize, using fiber reinforced polymers kind of and also kind of comparing it to using steel plates, we're talking about a very important point is obviously the self-weight. The fiber reinforced polymers are quite low in self-weight as opposed to steel, which is high. The application in here is by hand basically, as opposed to using lifting gear and machinery for applying steel plates. And in my point of view, something that adds obviously to the whole costing of the project is obviously the corrosion and the maintenance. We're talking when we're talking about fiber reinforced polymers, it's a corrosion-free material. Steel plates, because of the innate nature of the steel, it definitely requires protection. Also kind of strengthening the point and the different options that we discussed earlier when we're up against any structural strengthening project. We also kind of made a case study to kind of compare the different solutions that we have. The case study that we have here is the objective was to increase the live loading capacity of a simply supported beam with about 35%. And again, we kind of went through the three main routes, the three main options that we discussed before, using abundant steel plate, jacketing or member enlargement, and lastly fiber reinforced sheets, fiber reinforced polymers. Bonded steel plate has the design has actually opted for 6 millimeter bolted plate, which added about 110 kilograms of dead load, and it needed obviously to be placed and lifted by trucks. Member enlargement, the design opted for adding a couple of rebars of 16 millimeters, and also that needed obviously a concrete cover of around 110 millimeters. This added about a ton of dead load, and it needed obviously to be formed and cured. Using the fiber reinforced polymer sheet was literally one layer of resin bonded fiber reinforced polymer, 1.5 kilograms of dead load, and it was placed by hand. So obviously it was very, very appropriate to use fiber reinforced polymers in this instance rather than the two other options. Again, one of the other case studies that we've done is a project in Old Kent Road, and the aim or the objective of the project here was flexural strengthening. And as you can see in here on the first picture on the left, something kind of a site developed tool, if you will, to actually kind of control the thickness of the structural adhesive on the back of the carbon fiber plate. So obviously, as you can see in here, it's a wooden box. This is something that the contractor has come up with on site. It's a wooden box completely immersed with structural adhesive, and obviously they start with the plate from the top of the box, and as they pull it, they obviously use this saw in here to kind of control the thickness of the structural adhesive. And as they pull the carbon fiber plate from the other side, obviously you get a uniform layer of the structural adhesive on top of the plate, which is obviously quite the objective. Another layer of the structural adhesive is laid on the floor, and obviously you apply them kind of wet on wet. Apologies. You apply them wet on wet, and obviously you kind of use a roller to kind of pass on and press on the plate to kind of release all the air entrapment in there and kind of remove all the voids, and then all the excess material is actually removed, and this is what you end up with, a completely neat application of flexural strengthening. Also, again, to kind of summarize what we've seen earlier, and I think, in my opinion, this picture kind of tells us 1,000 words, really, when we're talking about structural strengthening in general. As you can see in here, this was a multi-story car park where the designer opted for member enlargement, unfortunately. So obviously this was an already restrained space in terms of obviously kind of headroom, headspace, and a space used by pedestrians. But the designer here, I'm thinking because of uncertainty, or because of fear about specifying fiber reinforced polymers, has opted for member enlargement, which has already added obviously to the very minimized space, obviously a less space. So definitely any other system for structural strengthening would have been more appropriate than the picture that we can see in here. Another point that I would like also to note in here, that there was, it's actually mentioned in the Concrete Society Technical Report 55, apologies, Technical Report 55, that there was a study issued by Network Rail that has indicated a cost saving of about 30% when using fiber reinforced polymers for structural strengthening as opposed to steel plates. So don't take it from me as a material manufacturer, take it from Network Rail, or actually completely unbiased, I think. Also, as we have noted several times, there are various disadvantages of using fiber reinforced polymers, and we say the first point here is obviously the perceived cost. And why do I always say it's a perceived cost? Because when we are dealing with a contractor, and we sometimes, the majority of us are coming from a contracting background as well, we always kind of weigh things by how much they cost, and this is why it's kind of a perceived cost. However, when now the new technology and the new knowledge tells us to kind of weigh the whole life costing of the project, and when we actually include and kind of think about the whole life costing of the project, using FRP for structural strengthening is not actually expensive at all when you include the whole costing of maintenance and inspection that kind of runs across the life of the project. There is definitely a lack of knowledge across the composite strengthening, because it's a fairly new technology. It's a fairly new application of this material for structural strengthening, and this is something quite understandable. And something that adds to that is unfortunately, until the minute that we are speaking now, using fiber reinforced polymer for structural strengthening is not actually covered by any British or international standards. This should be addressed in the new version of the Eurocode. I'm thinking that it has been addressed, but I haven't read it. I haven't had it. I don't know if it has been addressed or not, to be completely honest with you. But as it stands now, it's not really covered by British or international standards. And obviously, there's a huge need for skilled operatives in order for the application to be successful. Moving on to a very important point, in my opinion, the comparison between external application of fiber reinforced polymers versus near surface mounted application. What you have seen in the previous slides is all related to external application for fiber reinforced polymers, whether that is for flexural capacity, shear resistance, or axial loads, but all of them are applied externally. What we're talking about here is the near surface mounted application. Why do we use it? If we're talking about, if in this instance, we're talking about, this is a slab for multi-story car park, for instance, and we need to strengthen it for flexural capacity. And obviously we need to consider obviously the highest bending moments that are happening here. Under the soffit here is absolutely no problem. We could actually apply the fiber reinforced polymers externally, absolutely no problem. But when it gets to the top layer, the top part of the slab here, obviously if it is a multi-story car park, it's going to be exposed to wear and tear. It's going to be exposed obviously to pedestrians as well as cars. So you can't really be comfortable kind of specifying and applying a fiber reinforced polymer system and leave it completely exposed to vandalism, basically. And this is why we opt for, in similar instances, we opt for a solution called near surface mounted application. The solution basically is kind of mounting the fiber reinforced polymer solution into the concrete cover area. So obviously we kind of use grooves of about 20 millimeters, and we completely encapsulate the rods in these instances, in this application, the carbon fiber rods or the glass fiber rods, we completely encapsulate them with structural adhesive material. In this application, because as you have seen earlier, we don't have rods in our range of products, so we have collaborated with a company called Schuck. I'm assuming that this name is actually quite familiar to a lot of you, because Schuck is a German company that is specialized in the manufacture of glass fiber reinforced polymer rods. The rods that you see in front of you here, obviously they are ribbed rods, which play an important part into increasing the bonding and decreasing the slippage, obviously, of the rods from the structural adhesive. And obviously they can be provided in different thicknesses. We're talking about 8 to 10 millimeters of thicknesses, dependent on the design. This is one of the applications where near surface mounted structural strengthening has been used, and as you can see, it's literally the same application that we have discussed earlier. It's a multi-story car park where the parts where the most negative bending moment is actually taking place. It can't be lift exposed to obviously cars, vandalism, wear and tear. So we opt for obviously kind of mounting the structural strengthening system within the concrete cover. And as you can see, the chap here is actually cleaning the grooves and blowing air into them in order for it to be prepared to receive the encapsulating layer of structural strengthening, as well as the fiber reinforced polymer rods. And here we're going to discuss a few of the applications. Obviously, as we have discussed and as we have seen before, fiber reinforced polymers can be used for flexural strengthening. They can be used for flexural strengthening on normal concrete elements, pre-stressed concrete elements, post-tension concrete elements, as well as masonry and timber structures as well. I don't know about South Africa, but timber is quite common to be used. Timber and masonry are quite common building materials to be used in here in the UK. So this material can be obviously used for flexural strengthening. we have discussed before that when we're talking about stresses and strains, we said before that the most governing criteria when we're designing is going to be the strain rather than the stresses, because we're working in an ecosystem of concrete, of structural concrete, basically, where the concrete is the weakest element, and we need to adapt to that. So we only take a portion of the strains available in the fiber reinforced polymers, which is obviously the effective strain that we can see in here. And according to American Concrete Institute, this is how we can actually obtain the effective strain. The only reason I'm including this this equation here is kind of to tell you also that when we're considering flexural strengthening, there is kind of a soft point to the amount of layers of plates, fiber reinforced plates that we can add, because after this soft point, we're going to be spending a lot of money on the plates, but also gaining marginal increased capacity in the structural element. And how did we come up to that conclusion? As we can see from the equation that we can see in here, this is basically this is kind of to calculate the debonding strain or the effective strain. And as we increase the modulus of elasticity, as we increase more layers, we kind of, as we can see in here, we decrease the effective strain or the debonding strain. So as we add more layers, we get literally marginal increased capacity. And this is why it's important to note that the adding plates and plates over plates over plates is not the answer to increasing the structural capacity in flexural strengthening. The table that you can see in front of you, I took it from the Concrete Society Technical Report 55, and it can be used in all design situations. It kind of gives us the different factors of safety that are used in design when we're considering different fiber reinforced polymer material. And as you can see in here, the factor of safety of carbon and aramid are actually 1.1. And to put things into perspective, we're talking about a factor of safety for structural steel, the most commonly used material in design situations, is actually 1.15. So again, to put things in perspective, this is the factor of safety used for carbon is actually less than the one used for steel. This is the amount of certainty that the designers have for using carbon fiber reinforced polymer for structural strengthening. In this application here, obviously it was used for axial load confinement. And what's interesting about this application that you can see in here is there are two columns kind of with a very, very minimal space between the two of them. And because of the very small thickness of the material, the design here opted for structural strengthening of one column rather than two. And again, because of this very small thickness of the material, it was able to be extended between the minimum thickness between the two columns. If another system was to be specified and used, it would have definitely included the two columns together rather than one, because again, of the very, very minimum thickness that you see between the two columns. Also, one of the very important applications that we come across is obviously for shear strengthening. Obviously, when we talk about shear strengthening, the most effective method is actually full wrapping, but in the majority of applications, this wouldn't be possible because of the existence of another structural member on top of the beams, for instance, as we can see in here. So obviously, the most common shape that you can see for shear strengthening is actually the U-wrap, and sometimes you see only kind of side a strip on the side for shear strengthening as well. Obviously, dependent on the design, dependent on the amount of shear force that is happening in the joint. One of the most interesting applications also that we come across in one of the instances is the overturning force. For instance, imagine that this is a diaphragm wall, and for some reason we want to increase the structural capacity of this wall. And obviously, this is one of the instances where we need to be very careful of placing steel in close proximity to carbon fibers. In this instance, the designer kind of opted for using carbon fiber and a steel angle at the bottom of the wall to increase its capacity. So obviously, this is again, putting carbon in close proximity to steel will actually encourage the steel to create a corrosion cell, and this is why we always recommend using a separation layer, either of structural adhesive or an epoxy layer, or glass fiber reinforced polymer to come in between. Fire consideration is of high importance after the unfortunate incident. I don't know if you guys have heard about it, the unfortunate incident that happened in London in Grenfell Tower. Fire consideration has been baked into kind of an innate nature that we kind of consider in literally everything that we produce, starting from cement, concrete repairs, and obviously fiber reinforced polymers. The main reason why we consider fire and fiber reinforced polymers is because of the resin, is because of the epoxy. As we said before, it's a petroleum derivative, and it has quite a low glass transitioning point, so it kind of starts losing its strength at very low temperatures. And this is why it's important that when we're talking about a building or structure where fiber reinforced polymers is used and the building falls under fire regulations, it's very important to actually protect the fiber reinforced polymers from fire. The majority of applications that we've come through, there is no fiber reinforced polymer system that is designed to carry loads in fire. Absolutely, in the design, it's actually considered that in the case of fire, the fiber reinforced polymer actually will not be in action. This is why it's very important to check the serviceability loads, and it's very, very important for the building, the structure, to carry its own service loads on its own in case the fiber reinforced polymer system is in failure. The most important point to note in here is that if we are operating in a building where fire regulations are in place, it's very important that we protect it, protect the structural strengthening system using any of the fire protection systems. This is a case study that we have done in High Wycombe, and as you can see, it's a university where Sangaban efforts have actually come together. So as you can see in here, this is the carbon fiber plates being applied for flexural strengthening, and they have been covered by British gypsum fiber rated boards. This has given the fiber reinforced polymer system fire protection for 2 hours. And again, this system has been completely designed by Sangaban. As we said before, British Gypsum is a part of Sangaban, and we kind of applied this system under one umbrella. Very quickly, a few of the case studies for the football fans that are present within the presentation. This is quite a known structure, the City of Manchester Stadium, where we have applied carbon fiber reinforced polymers to increase the structural capacity of the terraced beams. This project was done years and years ago, and it's actually still in place at the minute. And you see the significance, the importance, the criticality of the application of fiber reinforced polymer here. It was kind of a problem solver, really, because of the very, very small space where the people and the contractor were actually operating. So it was quite an adequate system to be specified, and it's still in place until today. This is another project that we have done on the M60 motorway. Our client there was the National Highways, and as you can see in here, fiber reinforced polymers was used for flexural strengthening, and there was, most important point to take away in here is that there was a time saved of about 50% on the program after using fiber reinforced polymers. Again, because of the nature of the product is actually very high, very low in weight, very maneuverable. It can be used in a very, very nice and easy way. This is a project that I personally got involved with. It's a Slough cooling tower. As you can see in here, it's a gigantic project where obviously fiber reinforced polymers, carbon fiber reinforced polymer wraps were used actually to keep the integrity of the structure. The structure that you can see in front of you was fully wrapped from the outside, and from the inside of the cooling tower, it was applied on in a strips actions, obviously, and kind of a collar situation. So obviously this wrap in here, and then there's a space with no strengthening, and then there's another fiber reinforced polymer strip being applied. One of the important points to note in here is this was the existing condition of the concrete, very rough, and obviously it wasn't possible with the existing condition of the concrete to apply any structural strengthening system. So we kind of advised the contractor to apply a smoothing, obviously to grind all the irregularities out and apply a smoothing or leveling compound, as we call it, in order for the surface to be completely prepared and ready to receive the carbon fiber wrap. Application guidelines and some of the most important points to kind of summarize what we've discussed earlier. As we said before, the success of any application kind of relies heavily on 2 points in my point of view. Surface preparation is a very important point, and also the quality of workmanship goes a long way into the success of any fiber reinforced polymer project. And this is why it's actually very important for us to evaluate, understand what is the existing condition of the concrete, the existing compressive strength, the existing bond strength of the concrete are very, very important for us to understand. Also, one of the limitations of fiber reinforced polymers, for instance, if the existing concrete is of poor quality, for instance, the compressive strength is less than 20 megapascals, or there are voids or deterioration, there is corrosion existing in the concrete, we would never ever be able to specify fiber reinforced polymers. In this instance, we need to put the concrete right. We need to evaluate, come up with a repair strategy, put the concrete right, and then we can talk about increasing the capacity or protecting the concrete using fiber reinforced polymers. As we have said before, when we're talking about fiber reinforced polymers, it's basically a maintenance-free system. So visual inspection is suggested annually, merely visual inspection, with a detailed inspection that is suggested every 6 to 10 years. And again, this is not my recommendations. This is according to the technical report number 57, which we will discuss in the later slide. What does it entail exactly? When we compare that, the 6 to 10 year period, when we compare it to other structural strengthening systems, for instance, using steel plates or member enlargement, we're talking about a detailed inspection at least annually in order for us to kind of assess the condition of the concrete and assess the condition of the steel plate. Again, if we consider the whole costing of the maintenance and inspection, fiber reinforced polymer are going to be the cheapest solution. Design and inspection standards. Again, as we have said before, there are lots of guidelines out there. However, the design is not actually governed by an international standard as we speak now. It will be. There are lots of talks now, again, that it will be covered in the new Eurocode release. But as it stands now, the most important documents when it gets to the design is the concrete society technical report number 55. When it gets to the inspection and monitoring is the Concrete Society Technical Report number 57. These are 2 very, very important documents to have if you're in the field of fiber reinforced polymers. There are a couple of guidelines issued by National Highways 368 and 371 are also quite important. There's a serial report that kind of covers the use of composites in construction, also that is very important. And part 10 of BSEN 1504 covers the application part of the fiber reinforced polymers. This is all the guidance that is available out there, and we're hoping next time we speak that there is going to be a Eurocode covering for the design and inspection of fiber reinforced polymers. This will take us to the end of our presentation.